Okay, first of all, thanks to the organizers, Frank, Siva, Rajat, and Arijit, to be able to speak here on a topic that's quite a bit different than what we have seen this week. Now, there are many topics of another type, but today this one will also be a little bit analytic. So before I dive into explaining what all these somewhat unfamiliar terms on the title are, let me first say that this is based on three papers, of which the first two are joint work with Giovanni Conforti and Daniela Tonon, who are now both since last year at the University of Padova. And the final paper that has also been written together with Luca Tamanini, who is at Brescia University, also in Italy. Now, quite a lot of words here on the title that are unfamiliar, and somehow the work that we have been doing is somehow has arisen from the following thought. So if you study large deviation principles, and you do this for Gaussian processes, and you look at the path space large deviation principles, you see that for all these processes, you have a common structure in the large deviation rate function. So all of them somehow have in the large deviation principle a rate function where the rate is essentially a half times the deviation from the limiting trajectory that you expect, and you square it. And this holds for five-dimensional theory on RD. This holds for Gaussian processes on Hilbert spaces. This holds for Dawson-Gertner type large deviations on the Wasserstein space, etc. So in all these processes, you see a common structure, and that, of course, begs the question, can you then actually approach all these questions with a common proof? And this is what this work is about. And somehow, being here this week also, for me, is kind of a challenge. So we introduce a setting where somehow the basic structure is a metric space. And of course, this week we have spoken about various types of examples where, for example, you have a graphon space, which is also a metric space. So does the graphon setup actually allow for a diffusion process that somehow, if you would study something that would be somehow path-space large deviations for this process, would it actually fit the framework that I'm going to introduce today? Now, I don't have an answer to that, but that is somehow a governing question that I've been thinking about this week. And I hope you bear with me and see at the end somehow what is the technology that is being introduced. And maybe you can share this thought about, hey, does it actually apply to the metric spaces that pop up during this week? So let's go to the setup, and I'm going to introduce this Hamilton-Jacobi equation. And it's the following equation. And I'll introduce what this equation means from the perspective of large deviation theory. So if you've never seen it before, that's fine. We'll slowly ease into it. So path-space large deviations are related to Hamilton-Jacobi or even Hamilton-Jacobi-Bellman equations that come in two forms, either this one, where there is a time component, or this is the resolvent component. So if you ever work with the martingale process for Markov processes, it's kind of the same two equations that you know, where H is applied by an operator A, which is then the generator. And of course, you have the resolvent equation where also you replace H by A. And then you want to study these two equations, but yeah, then your operator is linear. Now, in my case, this operator is not going to be linear, but it's nonlinear because it has to reflect the large deviation structure. And in this talk, I'm going to look at a very specific one, namely one that is quadratic. So my operator has the following form. So I plug in, let's say, a smooth function f, and I do the following two things. So I take a square of the gradient, and the second term is a drift term. So I have some potential E. Think of an entropy, or maybe a confining potential, and I want to do the gradient flow in this potential. And this is somehow captured by this. So this Hamiltonian somehow, for those familiar with control theory, describes a controlled gradient flow. But also, I will explain exactly what that means. So the aim of the talk is the following. So the first thing I'm going to do is, why does this equation pop up in large deviation theory? And Frank already mentioned that at the beginning of the week. This is the somehow well-known, or not so well-known, Van Court's theory. So I'll talk a little bit about that. Then the second question is, why do I want to use exactly this structure? Because if you use Van 't Coort's theory for large deviations, you find all sorts of Hamiltonians, but why is it exactly this one that I want to study today? Do I have to do this? Okay, good. Then the third question, of course, is, okay, suppose that this pops up in large deviations. This is the structure that you want to use. Why do you actually want this general metric structure to treat many of these equations in one go? So that's the third question I want to answer. Then the fourth question is, okay, can we actually treat uniqueness of solutions for this equation, which is necessary to establish large deviation principle, just as we know it from the martingale problem. If you want to show convergence of processes, you show operators converge, you want uniqueness of the martingale problem in the limit. Yeah, so that's kind of the question here. Yeah. But if you go to do it more generally, then okay, then yeah, so the Gaussian structure has to do with a specific form here in 2. So if you go to more general processes, it will be more difficult. But the challenge here is to go to the metric space context. So that's why we stick to the most basic setting. Yeah. Yeah. Yeah, you need more than the maximum principle to get uniqueness. Yeah. We'll get to that. Yeah. Of course, I introduced a framework to get uniqueness of solutions in this metric setup. And then, of course, the question is, yeah, it's nice that you have perhaps a setup in which you have uniqueness, but if you don't have existence, it's worthless. Right? So the final question is to very specifically do this in the Wasserstein context, because this Hamilton-Jacobi equation is a lot studied recently in the mean field game theory world. So there is a lot of activity there. We wanted to settle this question for this community. So we picked the Wasserstein 2 case that actually for large deviation theory is also very relevant, because the Das and Gertner large deviation result holds in that context. So this is if you take Brownian particles on RD, you take the empirical measure, you send the number of particles to infinity, and then the limiting equation is the McKean-Vlasov equation, and you want to do large deviations around that, then this is exactly the context that you're going to pick up. And so our third paper is about existence of solutions in this setting. And in the future, we'll do it more generally. I'll say a few words on that later. Okay, so how does this pop up in large deviation theory? And for that, let's go to the simplest setting in which we can do this, which is the Friedlein-Wenzel type theory. So let's pick an SDE on RD or R if you want. And it has the following type. There is a drift term, which for this talk now I'll take to be a gradient. And let's take Brownian motion, but multiply with 1 over square root of n. So this fluctuates. So these fluctuations get smaller. And so we already saw on Monday in the talk of Rajesh that then indeed you expect a large deviation principle. Although there we did it for jump processes, here we do it for diffusion. But indeed, Friedlein-Wenzel theory says that the probability that xn is closest on path gamma is decays exponentially fast in terms of n, and then somehow how fast it decays depends on the trajectory gamma. And the rate function here is this quadratic form that I spoke about in the beginning. Namely, I take the path that I expect as a limit, I take the deviation, I square it, and that's my rate function. So this is the Friedlein-Wenzel large deviation principle. Now, I also want to look at this from a dual point of view, because that's what I'm going to use, and that is how the Hamilton-Jacobi equation comes in. So again, the same equation. And if you are a bit familiar with large deviation theory, very often, how do you prove large deviation principle? You look at exponential moments, you take the logarithm, you show that this converges. Now, in this setting, of course, we already know that there is a large deviation principle. So we know also that these log moment generating functions converge by Varadhan's lemma. So what are we going to get? That if I look at this object, let's also call it Vn of t. I do this because this is a semigroup in F in terms of the time variable t. This limit exists, and what do you get? you have the rate function that you evaluate in a path, and then I look at f in the final time. So the s is a typo, this should be a t. So I essentially look at all paths starting in x0 that go to, that I somehow optimize, free endpoint. I check how much the payoff is at the end. But then, of course, I have to pay to steer it in that direction. Right? And let me call this a limiting formula. Let me call it a Vt of f, because this is a control semigroup. Yeah, so I steer my path somewhere. I have to pay along the path. I can actually compose these things together. So this is also a semigroup. And maybe to make the connection to control theory, because this is a control semigroup, let's take one closer look at this one. So if you have a log moment generating function, you can apply duality formula. So this is convex duality. So the dual space of the space of continuous functions is measures. So I can re-express this object in terms of a supremum over path space measures, where you evaluate the expectation under Q of f at time t, and I have to subtract the corresponding entropy. Yeah, so I take the path space entropy between Q and my original measure. I evaluate it on this time interval from 0 to t. That's what I subtract. And then if you compare the two formulas, they are awfully similar. Right? So here we evaluate at the final time, you subtract the cost. And also here you evaluate at the final time, but of course there's randomness, so you take an expectation and you subtract a path space cost. Yeah, so in a sense, large deviation theory on a path space is corresponding to the convergence of control semigroups. And so if you go back to the setting that you might know, so maybe you have studied in the past convergence of Markov processes. The thing you then do is often you pick the infinitesimal generators. You show that these converge to some limiting operator. And you show that the limiting operator generates a semigroup, or somewhat equivalently has a unique solution to the martingale problem. And so here we see that the large deviation structure is embedded somehow in these semigroups. And then, of course, the question is, okay, can I approach this via convergence of semigroups? And can I approach that via the convergence of their generators? And this is the insight by Feng and Kurtz that built a theory based on that. So perhaps to recap, so in the linear case, let SMT be this semigroup of conditional expectations and let AN be its infinitesimal generator. Then what do? You show that the ANs converge and show that the limiting one generates a semigroup. And that then gives you your path space convergence result if you also have tightness. So let's follow Feng and Kurtz and do the same for the nonlinear semigroup. So we have this 1/n log expectation. Of course, this expectation is simply the Sn of the linear semigroup. So if I want to take a derivative, I can do this using the chain rule. Right, so I slap the derivative on that. I express it in terms of the linear one. Of course, the log will give me e to the power minus nf in the denominator. And in the numerator, I get the original operator applied to e to the power nf. And I still have this 1/n up front. And this I call my generator of the control semigroup Vn. Now, of course, I want this one then to converge. And so let's check that in an example. Yeah. Let's again go to this one. And let's look at its generator, right? We still have the drift term. We have 1/2n times the Laplacian. If I then plug in this formula, I'm not going to do fully the computation. But of course, we work with gradients applied to f. So by the chain rule, the e to the power nf goes through the operator. It's going to kill the e to the power minus nf. But somehow, if at the end of the day you assemble the terms, you find 3 of them. The drift term remains unchanged. The Laplacian remains unchanged. But I get a squared quadratic term. And if I now send n to infinity, I exactly pick up the operator that I wrote down on the second slide. Right, so if this one drops out, this is exactly what I had on slide 2. So I see by the large deviation theory in this context, I indeed pick up this operator. So what about the limit? I made two typos here, sorry. This should be a t and this derivative is not there. Right, so this is this control semigroup. And I want to take the derivative of that and I want to check if that indeed gives me the operator that I want to. I already gave away the second line, kind of. I want to take the derivative. And now, of course, this I cannot really do. I want to interchange the derivative and a supremum. Now, with enough analysis, you can actually make this rigorous, but this would take too much time. Anyhow, so let's assume that you can do that. Let's take the derivative, interchange supremum and derivative, and then compute the derivative of this object. Now, of course, the first term is simple because I get the gradient of f, and that should also be a t. Yes, yeah, thanks. So I get the gradient of f with gamma dot, and of course here I get whatever is inside in the final time. Yeah? So I get this, and now I see that this only depends on gamma 0 and gamma dot 0. So this supremum is actually simply a supremum over speeds. I get this object. This is a Legendre transform in V. And if I carry that one out, I get indeed the operator that I wanted. Yeah, so this is if you want to compute this, it's a quadratic optimization problem, not very hard. Yeah. So indeed, we see that these Hamiltonians converge, and this corresponds to the large deviation principle. So this was the insight by Feng and Kurtz, and let's take a look at what they roughly proved, which is the following statement. It's a long one. I'll walk you through it. And if you've ever worked with convergence of Markov processes, this is completely analogous. So I've written down a lot, but it's completely analogous to what you know. So let Xn be Markov processes. Take the generator. So this is a slightly more general form now in the martingale framework. Of course, beforehand, I just gave a formula, and now it more or less boils down to the same thing. So these are functions f, and then g is hn of f, such that this object is a martingale. So it brings it a little bit closer to the martingale formulation of convergence. And suppose that we then have the following things. Suppose we have large deviations at time 0. Yeah, we need to initialize somewhere. We have exponential tightness. Yeah, like always, we need some notion of compactness. Third one is we have convergence of operators, and the limiting one should be first order. Otherwise, it's going to be a stochastic thing, and then you don't have large deviations. And the final one is this uniqueness property. You want uniqueness of viscosity solutions of this equation.
Functions the Kraai.
Oh, that's my metric space.
Arbitrary metric space is true.
Yeah, so this is a very general statement. Of course, the difficulty lies in, hey, can you prove these other statements? Yeah. Okay. So if you have all of that, then you have path-space large deviations, and the rate function is a Lagrangian form. And so with Lagrangian form, I mean, so you have, for example, this squared thing where you take the difference of your derivative minus this gradient. So this I would call a Lagrangian, and this Lagrangian is the Legendre transform of this H. This is a very general statement, and hard to check the conditions. And especially this uniqueness of viscosity solutions. Yeah, so I'll spend some time on that afterwards. So on RD, we can do this. If you go to more difficult spaces, this is a challenge. Okay, so I introduced this now in the setting of RD, right, the Friedhelm-Wenzel type theory. So why am I now actually interested in a more general setup of spaces? Why do I want to generalize away from RD? And let's take a look at a list of examples. So if your spaces are not too hard, it's often pretty straightforward. So I can imagine if you work with the graphons like Anita worked on earlier this week, I'm not exactly sure how to do such a thing. But this depends on your example and what you exactly want to do. So if you have, for example, 2-scale Markov processes, like we saw in the talk before, if you want to average out over the fast component, then of course this also becomes harder. Yeah. So depending on what you want to do, it's either easy or hard. Yeah. Yeah. Like always, I guess. Yeah. Good. Okay, so let's go to a list of examples. So let me recap this equation. And of course, in RD, we saw what this corresponds to. You do five-dimensional type large deviations, this is what you get. I state the list. Let's go to the list. Not all of them might be familiar to you. The first one, the Alenkane equation, is an equation for phase separation that pops up if you look at Katz-Ising models. And you put it at the critical temperature. So you're very close to the moment that phase transition happens. Then the limiting equation is the Alenkane equation. And if you then do the large deviations, you get controlled Alenkane equation. So if you would like to do large deviations for that, you would like to have a comparison principle for this equation. Now, if you look at the Katz-Ising model, where instead of spin flips, you do spin exchange, you introduce an additional conservation law. And then this equation that goes with this is a Kahn-Hilliard equation. And the large deviation corresponds to the controlled version of that. If you have Brownian particles and you look at the empirical measure, and you take a limit, you get Fokker-Planck equation, or as you want, the McKean-Vlasov equation, and the large deviations around that, of course, correspond to this controlled. And there are two others. So the Karleman equation happens in systems, for example, an exclusion process with two layers. In one layer, the particles go to the left, in the other one to the right. And then afterwards, you squeeze the layers together. Then the Karleman equation is what you're going to get. So also there, you find this structure. And then the porous medium equation, I would actually not know how to get that with large deviations. But it's anyhow an equation in mean field games that is studied. And the interesting thing is that this gradient flow formulation only pops up by choosing your metric space and your energy well. So the type of physical law that you now want to study is actually reduced to finding a common structure, and then given the common structure, somehow embed the dynamics in the choice of the space and the potential. And this, of course, allows you to think, hey, suppose I take a new space, I take a new potential, what is then my physical law? So in a sense, there are many unexplored cases, and this is partly due, and so that's my question, like, hey, does the Graafmont space fit in this framework? I don't know. Good. Yeah. So, yeah. So let's go to our contribution and what is the history in this setting. So what is the goal? I want well-posedness for this equation, and I want to do it in a general framework that does not assume much more than, let's say, starting with a metric space and a well-behaved energy function. So that's my aim. So what has been, okay, so let's take an example. Why is this actually a difficult question? Perhaps answer that one first. So let's take the well-known Dawson-Gertner case, which lives on the W2 space, the Wasserstein space of optimal transport. And then let's look at this equation, and let's really pick the case that corresponds to independent Brownian particles. Yeah, in that case, the energy functional is simply the entropy. Yeah? Entropy with respect to the Lebesgue measure. If you think a little bit about this entropy functional, of course, if you plug in the Dirac measure, you get infinity. Yeah? So even starting with all the particles in a single point and then evaluating this operator, like immediately the framework breaks down. But if you run it for a little bit, you get a nice smoothened out measure, let's say with finite Fisher information to make it precise, then you can actually evaluate this thing. But anyhow, some of the point is that if I look at this object, for starters, this gradient is, well, even the function itself is infinity somewhere, let alone talk about the gradient. So the aim is to actually introduce a gradient-free formalism to treat this equation.
What is the gradient of Wasserstein space?
Yeah, that's a good question.
Which one do you take?
So it's an L2 object. So okay, so what you do is you yeah, kind of, yeah. Okay, so we want to create a gradient-free formalism so that I don't have to think about this. Establish it strong enough to get uniqueness to the Hamilton-Jacobi equation. And of course, then at the end, we somehow need to establish that this is a sensible framework and to establish that you actually also have existence, because otherwise it's useless. So some history. We are not the first to consider this. Now, I already spoke about in the Wasserstein space, in the mean field game world, people have been looking at this equation, but it's always in a setting where an entropy functional somehow contains a rho-log-rho term, because then you can reduce to somehow controlled Brownian particles that you control. And so in this setting, you can kind of lift your problem to a probabilistic problem, and then you can actually treat it. But that again means that you're restricted in this W2 setting. You cannot extend, for example, to the Graphon setup. So let's go to some methods that actually allow for some generalization and check what happened. So the first approach was actually by Crandall and Lyon that used functional inequalities to actually treat this term. So they did not have a gradient term, but they had a dissipative nonlinear operator. And then they used this dissipativity to treat this object. I'm not going to go very deeply into details, but it's very much based on the fact that you have a Hilbert space and that you very well know what this operator is. Now, later on, Jin Feng, the same Feng of Feng and Kurtz that I spoke about earlier, he was also interested in this problem because he wanted to prove large deviation principles in infinite dimensional spaces, and he ran into exactly the same problem. And so he worked with co-authors and treated two examples. So the Fokker-Planck equation, so the case with the interacting diffusion particles, but he assumed that these particles live in a confining potential that has superquadratic growth. If you have ever worked a bit with Wasserstein spaces, having a potential with superquadratic growth gives you a lot of compactness properties for free. And so if you just have Brownian particles, no potential, this is not an avenue that you can take. So their proof does not work for independent Brownian particles, which is a weird paradox, because that should be the easiest case, but falls outside of this framework. Now, later on, he worked with other co-authors on the Karleman equation. And also there is a compactness property that's being used that in general you don't have, and goes back to the Hilbert space setting. So what is now our contribution to this? So we do the following. And this is a very informal statement, and I'm going to explain a little bit what we're doing. So we start really with a metric space, but we want it somehow in the framework of Ambrosio, Gigli, and Savary, for those of you who ever worked with gradient flows on metric spaces. And then we have a functional E that has certain convexity properties. That's what we're going to do. Under those conditions, and I'm going to specify these a little bit more later on, then we have uniqueness of solutions. And in the specific case of W2, we have existence also. So two remarks. All the examples that I just mentioned in the list fall inside our framework. So I'm not hiding conditions that make it infeasible to check. No, all the ones that I mentioned fall inside this class. Now, of course, the question is, hey, you only do existence for W2. What about all the other cases? Yeah, this has to do with two things. We want to have existence so that the mean field game world people can now start using it. But the second thing is you need to be able to solve controlled versions of your gradient flow. And in the Wasserstein case, you can plug in simply PDE results that give you controlled solutions. And so you can actually import methods from the Wasserstein world. Whereas in a general metric space, of course, you need to come up with more general methods to do so. So this is kind of the thing that we ran into. Of course, in a Hilbert space, we can also do it, but we opted to immediately go for the general metric setting. Okay, so uniqueness of viscosity solution. So let's take a look a bit at what, in the first place, a viscosity solution is. Because, of course, I might want to solve my Hamilton-Jacobi equation, but the first thing you realize for nonlinear operators is that very often classical solutions do not exist. So you have to introduce a weaker formalism of solutions. And then, of course, you have many choices. Maybe you work on RD and you want to say, okay, my solution lives in a Sobolev space. Yeah, this is something you could do. But then, of course, you run into the problem that this only works on RD. And if you go to something slightly more difficult, your problem yet remains. Now, this was solved in the 80s by a group of people around Lyon that actually said the following. We want a notion of solutions that is actually based on the maximum principle. So we come back to the maximum principle that we spoke about earlier. You can actually develop from the notion of a maximum principle a new notion of solutions, and these are called viscosity solutions. So these are weak type of solutions that have embedded in their core that they come from the maximum principle. Now, I'm not going to do exactly this connection, but I'm going to define for you what the viscosity solution to the equation is. So I call a function u, which is bounded and upper semi-continuous, a viscosity solution to the Hamilton-Jacobi equation, if for any f in the domain, there is some x such that if the difference between u and f is maximal, then I have an inequality. I plug in u, and then of course here I would like to say that it's a solution if here I say minus lambda h of u is smaller than h, but of course u I cannot put in the operator, so I replace it by f in the point where their difference is maximal. So this I call a subsolution. Now for a supersolution I do the same, but I replace the sup by an inf, and I replace this inequality by an inequality in the flip direction. And then I call something a solution if it is both. Yeah, it's both the sub and the supersolution. Now then, of course, I want uniqueness. And so when is a solution unique? I want to introduce a slightly advanced concept for that. I say that the comparison principle for the Hamilton-Jacobi equation holds. If for any subsolution to the equation with, I've replaced h now by h dagger, and for every supersolution v to this equation with h double dagger, I have that the difference between u and v is bounded by the maximal difference between h dagger and h double dagger. Yeah, so it's a weird uniqueness concept. Let's take a closer look at it. Suppose that I have two solutions to the equation for the same h, of course. So u is a solution for h, and v is also a solution for h. Because u is a solution, it's a subsolution. Because v is a solution, it's a supersolution. So I can apply this bound. So I get u minus v is upper bounded by the difference of these two functions, but I assume that they were the same. So the difference is upper bounded by 0. But of course, I can flip the roles of sub and supersolution and get an inequality in the other direction. Yeah? So the comparison principle implies uniqueness. Yeah. And perhaps the second thing, so how can you think about this object? So what is the solution now? If you think back to this equation, and let's say that h was a linear operator, what is a solution? Solution is the resolvent, right? So if you're familiar with the terminology, the thing you get should be the resolvent. So if I look here at u is the resolvent of h dagger, whereas v is the resolvent of h double dagger. So the comparison principle actually translates into a contractivity estimate on the resolvent, which is of course what you expect. So this uniqueness concept is a bit odd if you see it for the first time, but it gets you uniqueness and it gets you contractivity for the solution map. So very nice. Okay. So let's try this in practice. So let's go back to the RD case of the Friedlein-Menzel setup. So we go back to our original example and check how you would actually do that. How would you prove a comparison principle of this type? I assume that most of you probably have never seen something like this. So let's go very slowly. So I want to estimate this difference. So that's where I'm going to start. Yeah, I'm going to start there. But what do I want to do? I want to compare my subsolution to a solution that is, well, in this case, smooth. So if I go here, I have nothing of that type, but I'm going to introduce a trick to be able to compare with something smooth. So I'm going to do the following. So I have u in x minus v in x, but now I'm going to turn this into 2 points, x and y. But x and y need to be close, because otherwise it doesn't really make sense. So, and this is upper bounded now by u of x minus v of y minus a penalization d squared x comma y. Yeah. I take alpha, let's say, larger than 1. And of course, at the end of the day, I want to send alpha to infinity. If alpha goes to infinity, of course, this distance must be very small. And so x and y, these optimizers x and y must be very small. So this actually kind of recovers what you would like to do. But of course, at this moment, I've introduced the smooth function d squared to compare with. So let's say that x alpha and y alpha are the optimizers. Now in RD, I don't necessarily know that these things exist, but let's, for the sake of the argument, assume that they do. So if that is the case, if this is the optimizer, I can do the following thing. I can fix y alpha and still look at optimization over x. So what do I get then? So this is the same thing as before. So ux alpha minus v y alpha minus alpha over 2 d squared. This is actually also the same as taking the supremum over the same thing here. But now only x is free, but y alpha, y is fixed at y alpha. Yeah. So this actually you can derive from that via 2 straightforward inequalities. But if you look at this object, you see what is happening. I have a point x alpha where u minus this object is maximal. But that's exactly the thing that I started with in the definition of a subsolution. So I get that ux alpha minus lambda of h applied to this function. Actually, I should also add the vy alpha, but that's a constant, so that is going to disappear. This is upper bounded by h dagger of x alpha. That's what I get. Now I could do something similar with v. So I could fix x alpha and vary over y. Then I get a nice equation where the infimum is attained when I compare v to some object. And then I can use the super solution inequality and get this object, this inequality. So v of y alpha minus lambda now applied in this thing with a minus is larger than h double dagger. Now, why is this useful? Let's take a look. We go back to the beginning. U of x minus v of x was upper bounded by this one with the minus alpha over 2 d squared. And this was equal to this difference minus alpha over 2 d squared in the optimizers. Well, alpha over d squared is positive, so I can drop it. And so I get this upper bound. Yeah, this supremum is upper bounded by this difference. But if I do that, I can use the upper bound that I get from this one, right? This one is upper bounded by h plus this part, and v is lower bounded by this plus this part. And if I assemble that here, I get the following. So I get the difference of the h's plus the difference of the Hamiltonians. Of course, if I send alpha to infinity, x alpha and y alpha are going to be close. So that will give me the supremum over h dagger minus h double dagger. And then the final thing that I need to control is this difference of the Hamiltonians. So let's check how that works in an example. So I need to control the difference of these Hamiltonians. So let's do that in this case. So this is the case that we started out with. Of course, alpha over 2 d squared is just x minus y. So if I take a gradient of this thing, I just get alpha times x minus y. So I can fill that out. So if I do that one, I get minus this gradient. I fill in alpha times x minus y here. And of course, then I do alpha times x minus y, but I have to square it. And then I find, of course, again, the metric. Yes, I'm missing a square here, but I find alpha squared times d squared. And with the other one, I find exactly the same. Minus the gradient in y alpha times minus alpha times this difference. And here again, I find d squared. So if I subtract these two metric components, they are going to cancel each other. So that is nice. So these components cancel each other. And what remains are these two terms in terms of the gradient of E. And now let's study these very quickly. So what is this? So why do I know anything of this term? Suppose that E is convex. And what does this look like? So this is E. So I have E of y here, I have E of x here, but E is convex. So what do I know? I know that E of y is larger than E of x, plus the gradient of E in x paired with x minus y. And of course, this object is exactly what we have there up to a minus. So what do we find? No, it's actually exactly the same, right? Because there we have x minus y, here we have y minus x. So we get minus the gradient E of x paired with x minus y is upper bounded by E of y minus E of x. So this is a very simple expression, simply in terms of a difference on the potential. Yeah. Well, up to an alpha. And if I do the same with the second term, I find exactly the same difference due to convexity. So they cancel. So I look at my estimate and I assume that my function is convex. I use this interesting property for convex functions and I immediately see that whatever I had vanishes. And hence the comparison principle holds. And I want you to observe two things here in my computation. I had two objects here in terms of gradients, but I plugged in a metric square type object. If I look at these two terms separately, I find that the quadratic term actually gives me the metric squared again. Right? This does not involve a gradient. And if I then look at this object, I find that that you can actually estimate it in terms of a difference of the potential itself. And this is the key catch to developing a general theory. If I look at this object, I actually don't need any gradients. Of course, I derived my estimates working with gradients, but at the end of the day, my estimates don't involve gradients. That's the catch. So I want a setup that is robust enough to let me pull off this trick without going through the computation with gradients. So let's see how that works. The first thing, of course, is that what we now see is that somehow we upper bound our Hamiltonian in terms of this estimate on the difference. Yeah, so we had this gradient term for the energy, and we upper bounded this in terms of the difference. But for the upper bound and the lower bound, you do this for different functions, right? For one, you work with d squared. For the other one, you work with minus d squared. And you're really bound, right? And so I want to go back to, let's say, establishing uniqueness for the Martingale problem. And if you actually go back to papers from, when was it? The 80s. There is a paper by Hazra and Williams where they study like a diffusion process in a cone with oblique reflections. There they also see that the original Martingale problem does not have any solution because somehow in the point in the corner, you have to match up too many boundary conditions. So somehow the collection of functions that actually satisfies all of that is empty. Okay, maybe constant functions, but right, so always working with one single operator to somehow study your Martingale problem, this is not an avenue that always works. This was also realized by Crandall and Lyon, but then on the analytics side, where they did something similar. And the realization is you can choose your domain, and for sub and super solutions, you don't need the same domain. So we replace our Hamilton-Jacobi equation by a set of Hamilton-Jacobi equations, one that describes for sub solutions, one that describes it for super solutions. So that's what we're going to do. So we have some formal h. Yeah, it's defined in terms of a gradient, and a gradient is ill-defined. So it's not really a thing that exists. But perhaps we can actually find operators h dagger, h double dagger that are somehow below and above this thing, for which we do have sensible expressions. And now, of course, the trick is to start with quadratic objects and use the bounds and expressions that we have seen in our computation that we did for the five-dimensional setting, and just postulate this as definitions. So the test functions that I want to use for h dagger are of the type I said. I want to have quadratic functions, just like in the proof that we just carried out. And for the other one, I do the same, but then with a minus. Yeah, so these are going to be my two operators. These are going to be the test functions. And let's see what happens. So we take again a look at this one, and let's bound the two terms separately. And I'm going to do it exactly in the way I just did. Right? So we have essentially seen what's going to happen. But now, of course, the question is, how far can you generalize these computations? Yeah? Because this will set the conditions under which it's going to work. So what about the gradient square term? Now, of course, if we work on a Hilbert space or RD, this is very simple, right? You take a gradient of a quadratic thing, what remains is whatever was inside. You take a square, or you get back your squared object. Simple. Yeah. So how far can you push this? And the first thing to check, of course, is, hey, let's do this computation on the Riemannian manifold. That's the first metric space that is worth studying beyond the Euclidean context. And I'm not going to do this proof because it's actually kind of annoying. But on a Riemannian manifold, this statement remains true as long as x and y are not in each other's cut locus. So what is a cut locus? Suppose your manifold is a sphere. If you start at the bottom, you of course get a point where the metric squared is non-differentiable exactly on the other side, because your distance increases until you hit the top point, and there you have like a local maximum to the difference from x. Yeah, so there you don't have differentiability, and then this formula fails. It doesn't really matter, because in the proof we saw somehow x and y need to be very close, so somehow you avoid these singularities. So let's just assume that we can do this. So on the manifold, this is okay. And perhaps an interesting one, on the Wasserstein 2 space, it was Otto that realized that there you can do this also. Now, if you have never seen it before, don't worry. So you take the Wasserstein 2 gradient of your squared Wasserstein metric. What you pick up is the L2 norm of the optimal transport map from rho to pi minus the identity. And if you square that, you find the Wasserstein metric squared. So also there, this holds. And I would call a space that satisfies this property a space that is infinitesimally Riemannian, because at almost every point you have a tangent space where you can perform a computation like this. And this is what is the Riemannian property. So what about the other term? Now we already see what happened. So E is convex. Then we get this inequality using convexity. That's the one that I wrote on the board there on the left. And so that means that this object is bounded by the difference of the potential values times alpha. Yeah. And perhaps more interesting, you might ask, hey, what if I have something that would pop up in the Alencane equation where you have phase separation, where you have a potential that is double well? This is not convex, but it's if you add a quadratic function sufficiently strong, you can turn it into a convex function. And this we call a semi-convex function. So if E is kappa convex, which means that the Hessian of this thing is lower bounded by kappa times the identity, then you can actually upgrade this inequality by adding minus kappa over 2 times d squared. Yeah? So this is still a gradient-free estimate and allows us to go to negative kappa. Okay. So this is also a general upper bound. Now let's ask ourselves the question, okay, in what type of metric spaces can you pull this off? Right? Because we still work with gradients here, we still get this bound. So when can you actually do this? And this was a work, very groundbreaking work from 2008 that built upon the realizations of Otto and co-authors, where they say, hey, if you have a metric space, we see that these gradients are ill-defined. Can we do without the gradients? Yeah, so the same question I'm asking now, but without the Hamilton-Jacobi framework. But they were the first to say, hey, I have something that looks like a gradient flow, but all my gradients are ill-defined, so what does this mean? And they figured out how to do this. So they look at a metric space where you have geodesics. So metric space with geodesics. And they say, hey, my functional is kappa convex or convex if it is convex along all geodesics. And then there is also a generalization where you plug in this additional kappa. And then, of course, I need to have a gradient flow because that's my limiting equation. They say, okay, something is a gradient flow for this energy functional in my metric space if the following holds. And they call it EVI, which is the evolution variational inequality, which in layman terms is just a gradient flow, but with additional properties. If, for this energy functional, if you take the derivative of the evolution of d squared along the trajectory, this is upper bounded by exactly this difference that we've seen before. Now, of course, if you do a formal computation like we did somewhere in the beginning, if you compute this derivative, that's exactly this object. Yeah? If the gradients exist, yeah? Which they often don't. Yeah? But this you can always formulate. There's somewhat of an if and only if. Suppose that you have these solutions, then actually E is also kappa convex. So you can somehow go back and forth. So I'm now going to formulate my kappa convexity condition on E simply in terms of, hey, there is this gradient flow in this form. Yeah. And perhaps, let's discuss about this later. Yeah. Okay, so what is now our Hamiltonian? Let's take of this form. Then formally we have this, these two objects, and now we have formulas for both. For the first part, we use the EVI upper bound. For the other one, we use the Riemannian structure, and this is the object that we get. And now our rigorous upper bound for our formal Hamiltonian is simply the operator that we get by pairing up all these F's with their images. Yeah? So H dagger, which is the upper bound, is going the pairs of F, and then G is H dagger of F, where F is this and G is this. And for H double dagger, I do the same, but with minus D squared. So let's go back to the comparison principle. Why would we have comparison principle in this case? Let's go back to this argument that we did for the RD case. So we start as before. We take this difference, we subtract alpha times D squared, we pick our optimizers. Then we know that we have subsolution for H dagger, supersolution for H double dagger. We do the same estimates as before. And to get this upper estimate, I need to establish that this difference, and then perhaps with the lim inf, is upper bounded by 0. But now, if I actually compare these two things, yeah, the squared metric things immediately cancel. The difference of the energy functions immediately cancel. The only thing that remains is some object, which is alpha times D squared with the convexity constant. I haven't really discussed about it, but somehow other arguments can show that alpha times D squared in this framework, that this actually goes to 0. So working in this framework gets us a comparison principle for a very general class of spaces. Now, one catch, and I do not have the time to go into this. Of course, I was always assuming here that there are optimizers. And then perhaps on RD you can say, okay, RD is locally compact, so maybe if I wiggle a little bit around, I can salvage this situation. But if you now work on a Wasserstein space or a Hilbert space or whatever is a metric space, of course, wiggling around will be pretty hard. Yeah? So this is where, of course, so this analysis is somehow, to some extent, intuitive and straightforward. Perhaps you see it for the first time and think, okay, what's going on? But if you work a bit with this becomes pretty intuitive. But somehow fixing this issue is the real trouble. Yeah? So how do you actually fix this? I'm not going too much into details. The thing you need to do is you have to actually add an additional part in your test function to be able to work around this. So the metric balls are not compact, so you don't find your optimizers. Now, how can this be solved? This was solved by Ekeland. He introduced a method to find semi-optimal points. So you have a point that is almost optimal, and then Ekeland found the method where you slightly perturb the function you want to optimize with, let's say, the metric itself. So not the metric squared, but the metric. And then you can find an optimizing point very close to your almost optimizing point. This is technical, difficult analysis. I'm not going into it. Yeah? Then there are some problems, and I don't have the time to discuss it. Anyhow, I'm going to introduce a metric-like object that can play the role into this Ekeland perturbed optimization principle. And I'm going to add that to the test functions. So it's not alpha over 2d squared plus c, but now I'm going to add b times this perturbation. And this has nice properties. And I can also get an upper bound where this b actually pops up here and here. But the final expression looks very similar. I'm not going to explain how this works, except that you can do it. And the thing is, I can work with very small b. So if I then somehow subtract the two terms, more or less everything is going to drop out, except here you have to work a little bit. But somehow a day of analysis, if you've never seen it, and half an hour maybe for me, you can show that this b doesn't really matter. Yeah. So comparison remains true. So this gets me to the comparison principle. If I have a metric space that allows for an EVI gradient flow, some property that E is somehow nice on the interior of its domain, then the comparison principle is satisfied. Okay. The two key examples. Let's pick the Wasserstein space with an energy functional that is, let's say, rho log rho, plus a confining potential, plus a pair interaction, where these three satisfy the McCann conditions. Maybe you've never heard it. These are conditions on growth and convexity. Then this is satisfied. The other case is, for example, the controlled Alenkane equation. So you do the Katz-Ising model in the critical regime, maybe with a double well potential in the limit. Then this also holds. Now, what about existence? I have 1 minute. Sure. 0 minutes. This Tataru distance of this perturbation with the B, this is not smooth. It's like a D. So if I want to establish existence, it's a mess. It's not nice. So what we do is we introduce two new operators that are defined in terms of cylindrical functions based on the D squareds. And then we show that the Tataru distance, this perturbation, can be obtained by taking limits of these ones, so that you actually have graph convergence. Yeah? To make that rigorous is 40 pages work, sadly, but you can do it. Yeah? Okay, so we have two new things. So what we know is a subsolution for this new equation in terms of these ones is also a subsolution for the original one. So comparison for the new equations follows from the old ones. And now we have smooth text functions. And in the Wasserstein space, we established existence. I'm not going to do it. But in the Wasserstein space, you have a candidate solution. It's the thing you would write down if you've ever seen control theory. This is your first guess. You write it down. This is the one that works. So we also have existence. And that means that for the Wasserstein space, we have the full package. So what did we do? I'm going to skip over this. But maybe some open problems. We only work for gradient systems. Yeah? What if your system is non-gradient? Now, a first candidate is a system, a class of systems called generic. And the idea is that your flow somehow orthogonally splits in a gradient flow and a Hamiltonian flow. And there are some techniques that somehow suggest that you can probably do it there as well. So that's an open problem. Our conditions do not work if you have non-local attraction or repulsion in the Wasserstein case. So there are some examples like the electrostatic repulsion or the Keller-Zegel attraction. There you do have a gradient flow, but it's not of EVI case, but weaker. Some of the question is, does it work there? And then finally, for which metric spaces can we pull this off? So we have a couple, but can we do it for graphons? Thank you for your attention.
Thank you so much, Richard. Maybe we have time for one question. If you guys want a 20-minute break, then one question maybe.
Apologies.
No, it's completely fine. We did start like 5 minutes late. So. Any question?
I have one comment. Graphons is being done by Somik Paul and his collaborators. They have a gradient flow with L2 metric.
Yeah. Okay. With a nice energy functional where.
L2 metric. Not the cut metric.
Yeah, let's discuss about that. Yeah.
Okay, if no other questions, then let's thank the speakers again for the first couple of sessions in the morning. And Siva has an announcement to make.